So we now know that position, velocity, and acceleration are related through algebra. But what about geometry? You may recall being taught in math class, algebra first, then geometry, then later some more algebra. But if you look back on it, they're not unconnected, right? It's not that there's no algebra in geometry and no geometry in algebra. So let's explore this a little bit. If we can establish that there's an algebraic connection, there needs to be a geometric connection. So let's see if we can see how that works. We'll start, as you did in geometry class, with graphing. So let's consider a graph of position as a function of time. Position is x, time is t. But for now, we're not going to do any numbers. We're going to do what's called qualitative graphing. Quantitative graphing, we'd have to measure things with a stopwatch and a meter stick and all that sort of stuff. But right now, I just want to look at the shape of the graph and see what we can tell just by looking at it. So here's my graph. I'm going to start here. I'm going to stay here for a while. And then, ever so gradually, I'm going to end up going up and then stop going up. Is it clear that this also gives us information about the velocity? Take a moment and be sure you see that the velocity is encoded in this graph. What the graph actually shows is where we were. We started here, and then we stayed here for some time, and then we began to move further up, away from the bottom of the graph. And as we get further and further away, time is still passing. So if there's distance and time, that's velocity. And then at the end, we're stopped. And you can tell that we're stopped, the same as at the start, because we're not getting any further from the bottom of the graph. So recall that velocity is equal to delta x over delta t. But on this graph, delta x is how much you move up the graph, and delta t is how much you move across the graph. And in geometry, we call that rise over run, or slope. So what you need to understand here is that we can tell information about the velocity by looking at the slope of a position graph. This velocity is 0 because the slope is 0. This velocity is 0 because the slope is 0. And this velocity here is not 0 because the slope is not 0. Also, note the curvature. What does that tell us? Well, let's consider that acceleration is defined as delta v over delta t. Now that is not so simply understood as being just the slope, because there is no delta v obvious on this graph. But if the velocity is the slope, think what happens if the slope changes. If the slope starts out at 0 and then gradually turns to a different angle, that change in velocity took some time. So this is related to the curvature of the graph. Do you follow? If the velocity is changing, then the tilt, the slope of the line has to change. And that takes time to happen. As the tilt is changing, that would be an acceleration. Then we have a more or less steady speed, because this is more or less a straight line. And then we have another acceleration here, where we slow back down. We were moving at a steady speed, and then we slow down and stop. So every time the velocity changes, by definition, the line has to curve. So the position graph actually tells us about the velocity and the acceleration, just at a glance, just looking at the shape of it. The steepness is the velocity, and the acceleration is the curvature of that graph. Now, the velocity is really easy to judge. We have a math formula for that. Also, is it clear that that could be positive or negative? If I continue this graph like such, this is a negative slope. You can tell that it's negative slope because as time goes on, instead of going up the graph, it goes down. So that's a negative delta x and still a positive delta t, because you'll always have positive delta t. Time only moves forwards. But position can go backwards. So positive velocity is uphill. Negative velocity is downhill. So far, so good? Remember, we've also talked about acceleration being either positive or negative. And usually, it's okay to just say, well, like positive acceleration means speeding up and negative acceleration means slowing down. That's not a bad rule of thumb, but it isn't quite always correct. Because here we have two negative accelerations. And I will try to show you why. I'm going to walk this graph. You ready? I'm going to start about halfway through the screen, right? And then I'm going to hold still for a bit, and then slowly start walking, and then stop for a bit, and then very rapidly go back to the beginning of the graph. That make sense? I move forward slowly, stop for a bit, and then very quickly backwards. Watch that one more time. I'm going to start in the middle of the board. Slowly forwards. Stop and hang out. Quickly back. Is it clear that there are three accelerations here? First, I accelerate from holding still to moving forward. Then I accelerated again from moving forward to not moving forward. And then I accelerated from not moving forward to moving backward quickly. Okay? This acceleration here is positive, but both of these are negative. And let's take a moment and make sure we see why. In order to get from zero velocity to positive velocity, I have to increase my speed in the positive direction. So increasing a positive velocity, that's a positive acceleration. Here, it's very clear why this is negative, because I had a positive velocity and I want to get rid of it. So in order to get rid of the positive velocity, I need negative acceleration. But this last one involves suddenly speeding up. And so your instinct is probably to say, well, that's a positive acceleration again. But since we're calling this direction positive, that velocity is negative. And in order to acquire negative velocity, I need a negative acceleration. I wasn't moving, and now I want some negative velocity, so I have to have negative acceleration to get it. Confused yet? Think of it this way. As I start to move forward, it's like hitting the gas, and then as I stop over here, that's like hitting the brake. But now, I want to go back where I came from, so I put the car in reverse, and I step on the gas. I'm speeding up. I'm using the gas pedal to go faster, but since the car is in reverse, it's still a negative acceleration. It's pushing me in the same direction that the brakes do. Okay? Now, all of that is really hard to keep in your head. And years ago, a student of mine, whose name I forget, came up with a really simple way of remembering which is which. Acceleration is related to the curve of the graph, right? Positive acceleration is happy, negative is sad. This curve is like a happy face, and both of these curves are curved like a frowny face. And that's a silly thing to think about, but it's really easy to remember. And now, at a glance, you can look at a qualitative graph and tell me where it's slow, where it's fast, where it's stopped, and where it's accelerating. In our next video, we'll actually try to practice this, but for now, I think that'll do.